Howdy and welcome back. So micro patterns. The micro patterns that we're going to be introducing here are from Craig Zillis's early slides for CS 126. In developing this class, I went through all previous content across multiple classes, and I really liked how he presenting this. So I'm going to go ahead and share it with you here. So one of the patterns that he introduced to his students was the most wanted holder. The name of this micro pattern, if you will, is going to be the most wanted holder. The problem that it's looking to solve is what we need to do to find the most wanted element of a collection. And most wanted can be defined however you'd like. It could be the largest element in the collection. It could be the one where a particular attribute has some specific value that maybe is a maximum within that collection. But irrespective of how you define most wanted, and that's kind of the abstract nature of this template is most wanted. What is it? That's not going to necessarily have a meaning until we go ahead and apply this to some sort of concrete problem, because then at that time, you know, okay, what it is that is most wanted about a particular element presented within a collection. Well, if we're looking for this, the solution here is going to be initialize a most wanted holder to the first element in the collection, compare every other element to the value in the most wanted holder, and update if the new value is better. So maybe you use something similar to this when you were looking at finding the minimum and maximum value for your I think it was the mounted pass assignment when we were taking those that data and creating a grayscale image from the elevation data. Perhaps this was, again, your solution for maybe the min. In that case, what is the most wanted element? The minimum value. What might be the most wanted element if you're looking to compute a max? The maximum value. But here's some C++ code down here. Assume you have some sort of standard library, vector of things or thing, whatever that is. I mean, we're leaving it open kind of here. We're just going to call it thing, and we'll name the vector things. It's a collection of thing. We'll go ahead and then introduce this most wanted variable to hold the first element in the collection. And then we'll go ahead and compare that element to every other element within it. So notice here, we've already got that at position 0. So we'll begin our iterative statement at index 1, and then we can do whatever it is to determine whether or not we've found a more wanted or more desirable object within that collection. Here, it looks like we're just checking or computing the largest thing within our collection of things. So we say, hey, if things.at_i is larger than, and that would be larger than is defined according to the user defined type, remember? So what that means is dependent on the type of object being employed. But anyhow, we go ahead and make that comparison. And if we find something better, we can go ahead and update most wanted to that thing. And that is the most wanted holder micro pattern. Okay, so now we'll talk about or introduce an additional micro pattern here. And you might have seen this before, might have thought about this before, but it's kind of cool to now provide or associate a name with it. So if you were talking about maybe how to solve this problem, you could say, well, just use the most wanted holder pattern. That would be a lot more clear than trying to kind of maybe explain what's going on here, perhaps. So the one-way flag. The problem that we're looking to solve here is simply we want to know whether some particular property is either true or false for every element within some sort of collection of elements. The solution here is we're going to initialize some sort of Boolean variable to one of those values, either true or false. And then we'll go ahead and traverse the whole collection, setting the Boolean value to the other value if an element we encounter violates the property. So if we go ahead and look here at the code I provided, we have a standard library vector of thing named things, same as last time. We have this Boolean variable, all valid, and we've initialized it with true. And then we're going to step through each element in that container. So we have a range-based for loop here, auto thing and things. So each thing and things, if thing is not valid. And this, again, is context dependent. So what I've written here is probably not going to be valid in your particular application unless the particular type of object that you're iterating through has this behavior that you can ask upon it, and that the result of that function invocation is sensible given the application where we're looking to apply this. So that conditional would be the property that we're checking against for each element in that collection. Here we're just asking thing, are you valid? And if thing in this particular case is not valid, we go ahead and set all valid equal to false, because at that point we would know that there is at least one element within this collection that does not satisfy the property that we were interested in. And at that point, because we found one and we were asking a binary question, yes or no, do all things within the collection abide or have this particular property? And because we found at least one, we can just break out of the loop, and then we could check what's the result stored within our all valid variable. If it is still true, we know that we visited every element in that container and that each element satisfied the particular property that we were interested in. If it was false, we would know that we found something in violation of that particular property. And again, this is one application where we were checking to see if something was true within this container. Well, we could have checked to see whether or not all of the items within things were invalid. And then only, so we'd start out all valid to false. And then if we found something that contradicted that initial assumption, we go ahead and update the variable, break out of the loop, and we could check at that point in the code thereafter to see whether or not what we were looking for was in fact true or false. So the next one is going to be the follower. Now, if you think about this one, you might have seen it before. And if you have seen it before, it might have been during the linked list assignment. So let's say we want to compare adjacent elements of a collection. Maybe we're walking through our linked list and we needed to find out where we were going to insert some sort of item. And if it's a singly linked list, remember that a lot of times, if we wanted to introduce, say, 9 in order to this linked list, we're not going to know the location of insertion until we've gone one past that element, depending on how you structure this. So you might have cur here, you might have prev here. And then once you find the case that cur's value is greater than the one that we're looking to insert, say it's 9, we know that we could say 9's next is going to point to cur, prev's next is then going to point to the node we were looking to insert. So not to get too off topic, but so we want to compare adjacent elements of a collection, or we just need some way to get back. So the key here is going to iterate through a collection, set the value of some follower variable to the current element as the next step. So in this case, we're looking at this through the standard template library vector. We're going to deal with things again. It's a collection of thing. And the first thing we can go ahead and do here is say follower is equal to things at 0. Alternatively, if this was dealing with pointers, a more sensible thing would be to initialize it to the null pointer. But anyhow, we could then go ahead and, I don't know, maybe we want to see whether or not each element within this collection was in order. So let's go ahead and assume that when we're talking about ordering here, we're going to think ascending. So each element, so the element at location 0 is less than that at 1, less than that at 2, etc. So I'm going to use a range-based for loop here to illustrate the utility of this. If you think about if this was just a for statement, we could kind of use the offsets with the indexes to visit the last element. However, that pattern doesn't necessarily scale if we're looking at something like a linked list. But just to kind of have something similar to the linked list example, we're going to consider one element at once. So for each thing and thing. And again, this isn't direct, like you can use this for a linked list, but there's a ton of different applications where the follower pattern can be applied. I'm just talking about the linked list in one particular application because I believe that it is something that you're familiar with. So again, keep referencing the linked list to hopefully make that connection, not because this is the only place where you can apply this particular micro pattern. So we are considering each thing within things. Notice the first time through, there is a self-comparison of the element at position 0 to itself, because in this range-based for loop, we're going through each element, and we've actually initialized follower to be the first element. I'm going to, kind of ignore this. It's one self-comparison. Whatever this, I think will continue. I think if we were to try to do something else with this initialization up here, it just makes it a little more confusing because you have to then check to ensure that follower is actually pointing to, or I guess in this case, initialized with some sort of thing object before we can make this comparison here. But anyhow, let's continue on. So if follower is greater than thing, we can set collection in order to false, and we could probably have just broken out at that point if the whole point of this is to determine whether or not the elements within this collection are in ascending order. Otherwise, if that check has been satisfied, if things are looking as they're in ascending order, that is, every element preceding the current element is at least less than or equal to the current one, we will go ahead and move follower forward to the next thing. And then when we hit the top header of our for statement, that will go ahead and move us to the next element in the collection. So this is how it kind of starts. Let's say we have a vector of a couple elements, 5, 6, 7, 8, thing, and follower, are they're the same object. They're storing the same integer value. I don't mean to keep saying pointing incorrectly, but I mean, we've been dealing with a lot of pointers here. So anyhow, yeah, these are just, we're literally copying the integer value into these objects. So that's iteration 0. Iteration 1 looks like this. So this is the second time through the loop. Oops. Follower is still here, you could say. Thing is now storing that element. And maybe, this might, I'm just going to continue. Okay. So that's the first iteration. And then here's where we can actually see that follower getting moved forward, if you will, but again, just assign the value at the first index. And then thing continues to move forward. But I mean, if you just think back to some of these linked list traversals, that's where we moved cur to curs next. But sometimes before we did that, we said prev is equal to cur. And in that case, prev would have been our follower. But we can see what's going on here, and it's kind of the same idea as if we're iterating through a collection and we need to somehow remember the previous element to make a comparison. If we don't have this nice vector data structure that allows random access where everything's laid out contiguously in memory, you definitely need some way of accounting for what came before you, especially if there's no way to kind of previously get back. So hopefully you can kind of see some of the utility of follower. Like I said, I'm quite confident most of you actually implemented something very similar to what it would have been if you had taken and applied this micro pattern to your one of your linked list assignments. So I guess just to close out this video, I know I've been rambling for a bit. I'll try to move a little bit faster. Design patterns focus on things at the object level. So many of the micro patterns that we've talked about here seem obvious, but again, there's a lot of power in simply giving them names, codifying a best practice solution to a particular type of problem, as well as, and we didn't really consider this for the micro patterns, but when we start to learn a number of them, you can start to think in terms of almost trade-offs. So here's a particular problem. What might be, what are the strengths of using one pattern to go ahead and provide a solution? What are the limitations of that? Is there a better pattern out there, sort of thing? And this kind of relates to the relationships between classes and objects when we start thinking about inheritance and composition, because again, this is all at the object level. So with that ado, let's move on to our first, I guess, I don't want to call it a full-fledged pattern, but it's a little more elaborate, a little more sophisticated than the micro patterns that we've seen today, because we'll see that it is really going to get on some of this, rely on some interesting relationships between the objects, both with composition and inheritance to successfully implement this strategy pattern. But let's go ahead and move on to that. I hope this micro patterns was a little bit fun. I think you'll find the strategy pattern pretty interesting. So I'm excited to share that with you.